Welcome to Lesson 14 of Applied Physics. This lesson covers torque and rotation. In this lesson, you will cover the following objectives. Understand terms and concepts related to the physics ideas known as torque and rotational motion, and understand the two conditions for equilibrium and the need for the rigid body model. Matthew, a physical therapist, is working with a patient who has a bad elbow. Every time the patient tries to lift an object of several kilograms, she feels a sharp pain in her elbow. Matthew decides to calculate the force on the elbow joint during lifting. He needs to do this at 3 different positions: when the angle of the elbow is greater than 90 degrees, when the angle of the elbow is at 90 degrees, and when the angle of the elbow is less than 90 degrees. How can this be done? If you were a medical technician, this could be a problem you would have to assess. How should you go about doing it? How will physics and the scientific process help you succeed? By the end of this lesson, you should be able to make the previously asked calculation. You will learn how to calculate torque about a point of rotation. You will understand the two conditions for equilibrium, and you will understand what the terms static and dynamic equilibrium mean. Notice in this diagram that you have a point of turning or a fulcrum labeled capital O, a force Fm, which is from the bicep muscle, and a force of weight labeled Fg from holding a 7-kilogram mass. Additionally, you have measured lengths from the point of turning for each of these applied forces. Using these measurements, you can determine the torques about the axis of rotation perpendicular to the elbow at point O. You will see the rest of the solution on another page. Examine the drawing and determine for yourself what is meant by the terms. If torque is equal to the perpendicular force times the distance from a point of turning, a common schoolyard seesaw or teeter-totter is a great example of an object which could have variable torques applied to it. A weight of 10 newtons is placed on a model seesaw at a distance of 30 centimeters from the pivot. Where should the weight of 20 newtons be placed to balance the seesaw? Notice that on the left of the seesaw you will get a counterclockwise torque, and on the right side you will get a clockwise torque. Setting these torques equal to each other would cause balance. Hence, we get an answer of R equals 15 centimeters. A ranking task is a neat way to look at a problem which has multiple variables such as weight, distance, and torque. When you compare variations in these measurements, you get a better feeling for what torque means. Shown on the next page are 8 identical seesaws. The girl of weight W sub 1 is always halfway between the pivot and the end of the seesaw. A boy of weight W sub 2 is to climb on the other side of the seesaw and balance it. The boy's weight is the same in all 8 situations. Rank the situations in terms of the distance from the pivot where the boy must sit in order to balance the seesaw. That is, put first the case where the boy is the least distance from the pivot, and put last the case where the boy is the greatest distance from the pivot. If 2 or more situations have the same distance, give them the same ranking. Review the two conditions necessary for equilibrium. Without these conditions, either an angular acceleration or a linear acceleration will be the type of motion that is present. Notice the monkey is hanging in a position of static equilibrium. The 2 weights in the monkey's weight are pulling down. The tension in the ropes pulling up are demonstrating the first condition needed. The sum of the forces need to be balanced. You can also look at the additional condition as the sum of the torques needing to be balanced too. Look at this image and imagine the result of these forces of given magnitude being placed in the direction shown. Is the object in a state of static equilibrium? What should you look at? You should try and sum the forces and sum the torques to see if they are in equilibrium. If so, the table is in a state of static equilibrium. The torque about an axis caused by a force, F, is always given by the product of the force and its moment arm. Balanced torques do not allow for rotational acceleration. Balanced torques imply a state of rotational inertia. Notice in the image there are three forces, each of which are acting along a line of action. A lever arm is also shown. If you multiply these values, you get the torque on the object about a center of rotation point. Are these torques balanced? The center of gravity is a geometric property of any object. The center of gravity is the average location of the weight of an object. We can completely describe the motion of any object through space in terms of the translation of the center of gravity of the object from one place to another, and the rotation of the object about its center of gravity if it is free to rotate. If the object is confined to rotate about some other point, like a hinge, we can still describe its motion. In flight, both airplanes and rockets rotate about their centers of gravity. A kite, on the other hand, rotates about the bridle point, but the trim of a kite still depends on the location of the center of gravity relative to the bridle point, because for every object the weight always acts through the center of gravity. Human bodies have different centers of gravity because the weight for each human is distributed differently. Do you notice the difference? We will be more interested in finding the center of gravity for simple geometric shapes, maybe even a wind turbine blade. Here is how you can do this. For a general shaped object, there is a simple mechanical way to determine the center of gravity. If we just balance the object using a string or an edge, the point at which the object is balanced is the center of gravity. Another more complicated way is a two-step method shown on the page. In step 1, you hang the object from any point and you drop a weighted string from the same point. Draw a line on the object along the string. For step 2, repeat the procedure from another point on the object. You now have two lines drawn on the object which intersect. The center of gravity is the point where the lines intersect. This procedure works well for irregularly shaped objects that are hard to balance. Let's start by determining what is the weight of a ruler. If we assume it is a uniform ruler, we know the center of mass. The location where all the weight appears to be will be exactly at a midpoint from one end to another. By placing a fulcrum at point A, you can easily use known weights to balance the seesaw device. Using the equations for torque and realizing that there is a ruler weight, which is unknown to you, at the center of mass, you can set up the equation at torque clockwise equals torque counterclockwise and solve. Try it at home on your own. Non-perpendicular forces need to have the components of forces separated into horizontal and vertical values. This can be done using trigonometry. Using either the sine or cosine function, you can split the forces from the tension pulling down on the horizontal meter stick this way. An example is shown on the next page. How would this work in a problem like the one shown on this page? Again, balance the torques in the equation. The sine theta gives you the perpendicular component of the counterclockwise force. The clockwise force is already perpendicular. Look for similar examples in your textbook. A 75 Newton force is applied to a wrench handle at a point that is 20 centimeters from the axis of rotation. What does the torque do to this force if the force makes an angle of A 90 degrees, B 75 degrees, or C 45 degrees with the handle? Each of these examples has the basic equation of force times lever arm distance when the force is either perpendicular to or a component of perpendicular to the lever arm. Therefore, you can take the 75 Newton force times sine 90 or sine 75 or sine 45, and multiply that times the 20 centimeters, which will give you a torque in the units of Newton centimeters. The diagram shows a box-end wrench fitted onto a nut. The same magnitude force can be applied to the handle in any of the 5 directions shown. Rank these directions in terms of the largest to the smallest clockwise torque produced. Again, the best method to do this problem is to take the perpendicular component of force and multiply it times some handle length. Since each of these forces are applied at the same lever arm distance from the point of turning the larger perpendicular force, the greater the clockwise torque will be produced. Can you answer this question on your own? When the point model for an object is insufficient, a new model must be used. The next level of idealization is to consider the object to be a rigid body. This means that the object is treated as if it maintains its shape no matter what forces act on it. Of course, real objects bend, flex, deform, or break depending on the conditions it is subjected to. But the rigid body model works well as long as all distortions are small compared to the dimensions of the object. The construction of a free body diagram for a rigid object starts with the drawing of a shape that is essentially that of the real object. As an example, consider the crane boom in the figure. The crane boom will be assumed to have a negligible mass and will be modeled as a straight line, with force vectors attached at the contact points for the cables and the hinge. Later, you will learn how to include the weight of a rigid body where it cannot be assumed to be of negligible mass. When constructing a free body diagram, first sketch the situation and select the object of interest. This is the real-world representation. On the sketch, circle the points where the object of interest touches other objects. These are the points of application for the forces. In a separate space, draw the rigid body model free body diagram of the object of interest. This is the physics representation. At each contact point, show the contact force as a vector in the proper direction if the direction is known, or as a pair of perpendicular vector components if the direction is unknown. If any non-contact forces are present and important, show their force vectors at the given positions. The method for determining the proper position for a weight vector will be discussed later. The next step is to develop a method of using this rigid body model to describe the behavior of real objects. The key idea is that the forces do not all act at the same point. The method we use to analyze the effects of those forces must take this fact into account. When we model a real object as something other than a mathematical point, we can show the forces acting at their actual points of application. Then we must look at how applying forces at different places affects the object. The basic effect of forces applied at different points is to cause the object to twist or turn. Think about how your hands on a steering wheel cause the wheel to turn, or how a hand on a wrench can tighten a nut on a bolt. Using the rigid body model allows us to establish a way to measure this twisting effect. The quantity that measures the tendency of a force to cause rotation is called torque, and is given the symbol tau.